So it's my pleasure now to move us along to the next part of our program, which is the first of our keynote presentations. And this will be done by Fred Pelletier, who is the Chief Scientist for Space Situational Awareness for NorthStar, Earth, and Space. Now, I'm going to read you a few details about Fred, although Fred said it would be okay if I just said, here's Fred. But I think there's more to it than that, if you'll permit me, Fred, just a couple of minutes. They're his minutes I'm taking, so I have to ask. He is the Chief Scientist, as I said, for Space Situational Awareness at NorthStar, Earth, and Space, a private Canadian company offering solutions to ensure the sustainability of Earth and space. He has been a key architect of NorthStar's satellite constellation and data processing platform, designed to continuously monitor multiple orbit regimes with unprecedented speed and precision. And while I'm thinking about it, is there a way we can dim the house lights so that his presentation will be more visible? I'm sorry just to float this out there in the middle of... Anyway, I'll check up on that once I get down from here. Fred has been at the forefront of space object tracking for over 20 years. From 2013 to 19, Fred led the navigation team for NASA's New Horizons mission to Pluto and the Kuiper Belt, where he guided the space probe for the Pluto system encounter in 2015 and the Kuiper Belt Arrokoth encounter in 2019, marking the furthest and most primitive object ever explored by a spacecraft. Fred was also a lead navigator for the Cassini-Huygens mission to Saturn, the InSight and Curiosity Mars landers, and the Near-Earth Asteroid Rendezvous mission to Eros, establishing scientific and technical expertise in object state estimation, spacecraft guidance and navigation, and optical image and radiometric data processing. In 2018, the International Astronomical Union accepted Pelletier as a permanent name for asteroid 17772-2005-DJ205, which I'm sure many of us are familiar with. Recognizing Fred's contributions as navigation team chief for the New Horizons mission to Pluto. In further recognition of his achievements in space navigation, Fred received the 2019 CASI Alouette Award from the Canadian Aeronautics and Space Institute. So without further ado, here's Fred.
All right. Does this work? You can hear me? Merci, Jeff. Ça me fait vraiment plaisir d'être ici aujourd'hui pour vous parler de mon projet, de ce que je fais, puis vraiment de participer à la communauté scientifique et technologique du Canada. Je pense que tout le monde ici, on a un rôle à jouer ensemble sur la gestion du trafic spatial. Et c'est de ça que je voudrais vous parler aujourd'hui. Mais spoiler alert, je n'ai pas pu résister, je vais vous montrer une image de Pluton. C'est trop... OK, alors, comme j'ai dit, et j'ai-tu le clicker pour... où est-ce que... Ah, il est là-bas. OK. Comme j'ai dit, je vais parler de space traffic coordination and the challenges that we're facing with that. I chose the word coordination on purpose because I'm not in the business of managing space, but I'm trying to help coordinate it. So just to set up the stage, I think it's pretty obvious to all of you guys that we cannot live without space anymore. It's in all our lives. Sometimes we realize it, sometimes we don't. I won't bore you with the details and how you navigated to here, if your weather was okay, blah, blah, blah. But we're all here because space is important. It was established by Wall Street Research that by 2030, the global space economy might reach a value of $1.4 trillion US, which is an impressive amount of money. And so we're in a very expanding market that's important to not only continue but to protect. Launches in space are progressing dramatically. There's nothing new here. I'm just stating the obvious, but you've all heard of the Starlink going to space. I think they're at 3,500 or so, but they want to get to the an impressive amount. There's Kuiper launching OneWeb, and there's the Chinese who actually decided that they're going to launch 13,000 satellites as well. So essentially, the problem we're facing is congestion into space, and this chart shows numbers from the European Space Agency. Colleagues of us that I'm sure you all well know that we talked often with. In fact, we have discussions with people in this room, like Gennady at CSA, on those topics. But my point is to show you the alarming growth of projected object being launched into space soon, and there's no reason not to believe this will not happen. It looks catastrophically, alarming, but I don't think anybody is going to stop Elon Musk or Jeff Bezos tomorrow from doing these things, and we better do something about it. So the congestion is a real threat. I like to actually use a couple terms to describe the problem. First is infestation. We've infested space with debris. They're out there. ESA estimates that, and NASA also corroborates, a total of 128 million objects of between a millimeter and a centimeter size. That's an impressive amount of things that can, break your satellites, threaten humans' life, and so on and so forth. So further to that, we've infested space, but there's also the domino effect that could cause catastrophic series of collision. We call this the Kessler syndrome from a NASA scientist, and I would like to think you've all heard about this before, but there are indications that this is a real threat and it's going to happen, and so far we don't really have methods to clean it up, but there are promising solutions, and I think we have to work together on this. It's going to be the main message of my talk. The second label I like to use is anthropogenic pressure. That only means we humans are deliberately putting more pressure into this domain by launching more satellites, but also by conducting ASAT events, for example, anti-satellite tests. There's numerous nations who have done this so far, and even the U.S. has done it. This is the kind of stuff that really puts space in jeopardy as a sustainable environment. And if we don't do anything about it, I'm not sure we're going to be meeting here for long, because there won't be anything to do. So the threat is real. I'd like to show you a video from my colleagues at NASA. We're working with the Johnson Space Center, Dr. Heather Cowarden over there, who created a laboratory experiment. You might have seen this before, but in case not, it's worth seeing. They put a microsatellite of 56 kilograms or so into a chamber and threw a debris at it, a bullet. It was a 8 centimeter size cylinder made of aluminum, and they just shot at it with orbital speed of 7 kilometers per second. And let's hope this works. We'll show you what that did. So the idea was to characterize what does a collision in space do with the right material of satellites. So the satellites was, of course, not a real one, but it was built using the real material. And they have put foam on the side to collect the debris that was caused by this. And essentially, I wonder if I can go back. Play it again. They collected 85,000 pieces of debris on the foam pads. That's just one collision, and we know history with Iridium Cosmos, the ASATs. So I think the 128 million is not a joke. It's for real. And these are threatening our cool satellites. So we're really facing an environmental governance challenge. And what we need is a legal framework to coordinate space traffic. The idea is the world, not just a nation, but the world needs to define a decision support system to do that. And I believe that we, engineers and scientists from all over the world, but yes, in Canada, have a really important role to contribute to this. Let me talk about a few legal challenges that we're facing. There's international tension. National security problems hinders on the ability of country to cooperate. Pretty obvious that the US working hand in hand with the Russians and the Chinese to fix problems is not obvious because of space became a military domain recently. I mean, you've all heard of the US Space Force. The French did the same with the Commandement de l'Espace, and even Canada has a division for space now. So like it or not, it is a military domain, but it creates big challenges to fix this problem. Also, government reaction to regulate, form laws, make treaties is a very lengthy process. So it takes time, and I don't think we necessarily have all that time at our leisure to fix this. So my pitch is to do a bottom-up approach where we as a community uses what exists today in terms of good practice and examples of things we can do to really build a better space traffic coordination system. And at the core of it is having more verifiable, usable data. So this quote that I'm showing on screen was from an article I picked up from the 2016 war game. So some person wrote this that because of creating a U.S. space traffic management concept is such a daunting task, it will be critical to use existing regulatory regime, agreement, and organization on a basis for striking the correct balance between ensuring operational safety and allowing for growth of an emerging industry. This approach has been used successfully in the maritime and air domain. So I share this quote, and this is only the first half, because of two things. First one, I like the idea of understanding what happened in the maritime and the air traffic domain. So allow me to talk about air traffic control a little bit. Air traffic control began in 1920. The first controllers in the United Kingdom started there. And it took nearly 3 decades or more to really create the regulations that we have today that control space, not space, air traffic. Let me give you two dates that are, I think, quite interesting. 1922, there was a collision in Normandy in France of two aircrafts that created a panic. I mean, obviously there was a problem with air traffic, and we're at the very beginning, 1922. So that started the process. But then in 1956, 34 years later, there was a collision. You might have heard about this. There was a collision of two airliners over the Grand Canyon that killed hundreds of people. And at that time, there was air traffic control at the airports, but there was nothing in between. So people were relying on the see and be seen principle. So pilots essentially had to just watch for themselves. And I think it's quite interesting. To make an analogy, I'm going to bring back the graph from ESA on the growth of object in space and compare it to the air traffic. So the graph on the left is from air traffic. And the two dates I mentioned, 1922 and 1956, are the far left, at the very shallow end of the curve. And then we all know what air traffic is today. And of course, after the 1956, serious regulation happened. The FAA took over. A lot of good radars were deployed to track everything. So, but it was done in time before the growth of the market. And in space, we're actually at the tipping point of the exponential curve. So I can't help but think what's going to be our 1956 event. I would say that Cosmos Iridium in 2009 might be the equivalent of a 1922 Normandy plane crash, but something's going to happen soon if we don't do anything. And this whole trillion-dollar economy that we enjoy, work very hard for, may not happen if we don't fix it. But the good news is there's a lot of talks and lots of, even here at this conference, a lot of people are paying attention to this, so it's encouraging, but yet challenging. Okay, so moving on. The second part of the quote I mentioned was about the bottom-up approach. I'll read it. It's more likely that once a U.S. space traffic management concept is ready to be shared with other nations, this bottom-up approach will be implemented faster and more effectively than a top-down imposition of a global STM concept. So that's kind of what I said earlier and where we can play a role. There's a couple examples I can think of things that are happening. There's the space sustainability ratings that are starting to emerge as guidelines to how to correctly behave in space. There's the net zero space initiative that NorthStar is proud to be part of. The idea is to take urgent action now to contain the pollution by 2030. It's quite ambitious, but we need those kind of things. But the main message I want to say is in the bottom-up approach, I think commercial is the way to really bring the foundational missing piece, which is more verifiable data. And that's what drives me to work at NorthStar in the SSA. But there's a lot of challenge to do this, and I'm going to talk a little bit about that. First of all, when you start tracking space object, there's a pretty impressive ground infrastructure in place right now, mainly led by the US government, but there's a lot of private companies like EXO, Leo Labs, who are doing similar object tracking. But I believe we're facing a reality that it's a bit limited because of a few factors. And I want just to illustrate a couple of them here. First of all, weather. You can see on this map how cloudy our planet is. And a lot of these sensors are optical telescopes. And they are obstructed. So it doesn't really scale up. You can put more telescope, of course, but really looking at this, to me, the solution is to get above the clouds. A second problem may be the denied territory factor. It's very easy maybe to have a super network over North America or Europe or even Australia, but that's just a fraction of the globe. What happens with the ocean? I've heard crazy stories of the US Navy putting radars on ships today to try to track more objects. Very complicated, not sufficient. Putting infrastructure over Russia and China is also complicated for the reason I mentioned before. So this all leads to a lack of revisit time and precision, which really cause a huge number of false alarms and collision warning that we are facing today. So owner-operators are inundated by collision warnings that they don't quite know or trust, and it's a bit of a zoo. So I joined NorthStar with the vision to fill the gaps. And our idea is to go to space. It's been done before, don't get me wrong. We have actually great assets in Canada who are experimenting with that. NeoSat, Sapphire Military, and there's numerous projects. That's great, but our vision is to be a bit bolder than that and go global. And we will launch a fleet of 24 satellites in 8 different orbital planes to look at space debris in a passive mode, survey mode, to track them all in all orbit regime. But what I just said is great, but yes, very challenging. It's not easy. We have a team of software developers and astrodynamics engineer working this problem, and I can tell you they're working really hard. We have a few of them here. That's great to have them, but they're taking a break from their daily lives where they work and crunch numbers a lot. In any case, I promised a Pluto picture, and let me just put it in context, because it's the birth of NorthStar came from not just me, but the team I worked on before on New Horizon. And New Horizon, my job there was to navigate, right, to get there. How do you do that? And I did the same thing with Cassini before, to Saturn, sorry. And we were using an optical camera on board to process imagery to basically find out where Pluto was. And in the case of Pluto, the biggest challenge was an ambiguity between the position of the spacecraft itself and the position of Pluto. So in the case of Pluto, as you know, it's very far away, so it hasn't been observed in its orbit very long in history. So the radial distance was poorly known. Plane of sky, fine, but radially, not so much. And on the other side, from our camera point, our spacecraft attitude control was with thrusters, and those thrusters were unbalanced. And so there was residual thrust that was pushing us around, and it was very challenging to figure out, is that thing really behaving like we think it is? So when you take images, you process them through image processing, you get metric data, you're looking at biases. It's like, is that real? Is that Pluto being away, or is it me? So you solve that problem by experience, a lot of analysis, and a little bit of humility, because you don't know everything. So orbit determination, navigation is not a precise science, it's a statistical science. And we used to call this at NASA the OD magic, or the voodoo. So we were turning knobs and just, so we did a great job, but it's not necessarily obvious. So I'm pointing this out because for every mission, whatever your field is or you're working on, you're facing with the same challenges. But doing this, finding a way to Pluto using optical camera, you're looking at a very, and especially for the Kuiper Belt object after, very faint object, distant. It's kind of like looking at objects circling Earth that are small. They're closer, but they're small, so faint. You're dealing with low signal-to-noise ratio problems. Do you need to stack images? Do you need to clean up, remove the stars, all that stuff? This is experience that we have, and that's our concept. We're going to scale this up to help solve the SSA problem. This is an image just for fun of the Arrokoth object after Pluto. So on the left, you see a stack. I think it was 20 images we had to stack in order to get the signal high enough before the noise level so we could see the thing. But of course, you're oversaturating stars, so we had to deploy star subtraction algorithms. So that was specific to this problem. We didn't have to do this for Pluto. We had to do this for the KBO, Kuiper Belt object. And in the middle, you see where the cross is, where we had the detection, and there's a zoom in version, and that's what we could use to correct the position. So my point is that those challenges are specific to the mission, and they were different for Saturn. They are different for a ground-based telescope looking at a geostationary satellite. They are different for something looking at LEO. They're different for space-based. Yes, very challenging, but every problem can be solved, and that's what we want to do. But at NorthStar, how do we do this? The idea is to really use a different concept of operation. So we're sweeping the sky, object is going to move, so definitely we needed a larger field of view. So that was the requirement on our payload are very, very strict. And there's lots of cool payloads around, but they each have problems. Sometimes it's power, sometimes it's field of view, sometimes it's the detector, whatever. Finding the sweet spots is difficult, and there's lots of promising technology advancement that we want to work on NorthStar. And I'd like to work with you guys on this. There's a lot of optical people in this group that can help us. I'm thinking of ABB, Nuvu, others. It's just the beginning, right? Okay. This is I wanted to show a NorthStar processing animation. So this is a data that was delivered to us by the Air Force Research Lab on a breakup on orbit. It is a simulation, but we threw in our algorithms to see if we were able to make detection. And we haven't worked intensively on that problem because it's not our CONOPS, but at least we're able to do the detection. And back in, when was it, 2021, November, when the Russian ASAT happened, we got a set of images from Numerica Corporation, who's now Slingshot. And we were participating in a SSA event led by the US, but we were actually in Europe doing it because it's a worldwide problem. And we got our engineers and scientists trying to, make sure or test the algorithms. Can we detect something? And I wanted to show it here. And I had one of my guys work on it. But it turns out it's not the best visual. I mean, the detection are happening, but I thought this was a bit nicer to show. Okay, so then the last challenge, or the next step, is the big data. Obviously, flying one spacecraft, looking at one object, you can get a team of people crunching number, working late nights and fixing this. Tracking hundreds of thousands of objects from a space-based constellation, it doesn't work. So we need automation. So we need a lot of software developers. That's why we have a big team of people who are simply taking the algorithms of what we're doing, helping, discussing with astrodynamics people to understand the concept, to turn the knobs and automate the whole thing so we process everything automatically. So we are going to process every 8 minutes a flow of image from each satellite dump that we're going to get to really refresh the catalog of what we see and detect, hopefully, unknown objects that are going to be new to track. How am I doing on time?
Very good. We have 12 minutes.
Okay, excellent. Yeah, this is sort of my conclusion. So we have chosen a different perspective to fill those gaps. It's a bold and ambitious mission, but based on experience, it's going to work. But it's going to require a lot of effort, and we're in this. I also want to say that NorthStar is not the only one. Is not the entire answer to the space traffic coordination problem. We want to work with our partners, yes, but also everybody. Because if we don't come at this together, we're not going to solve the problem. So that's why we like the term system-a-system approach. So NorthStar is a system. Leo Labs is a system. They're our competitor. I don't think they're here, but we need to work together. I need to work with other payloads manufacturers that are here to solve this problem. And bringing all this together is really how we're going to solve this problem. System-a-system means multi-assets, like I said. So stuff on the ground, stuff in space, radar, optical, passive RF. We have to be multi-domain. It's not just a civil problem or a commercial problem, but also military. You like it or not, this is the reality. And we also need to be intelligent about how we bring the data together to organize it, qualify it, and integrate it together. It's not a simple task to do that. So I think that together we can absolutely develop precise, verifiable data that will be the basis of space traffic coordination problems. So that's the bottom-up approach. One last slide, Jeff. Space is a global commons. The tragedy of the commons is when people overuse public resources for their own self-interest, ruining those resources for everyone. That's a bit what's happening in space. I would conclude with a bit of philosophical thoughts inspired by my dad. Our society is built on a powerful heritage of tradition. The Greeks, like Aristotle, taught us to the power of logic. This civilization took the myth away and wanted to work with what's real. The Latin then took that and learned the power of building things, engineering. And throughout history, humanity has, evolved like this. In the Renaissance, we saw an explosion of scientific achievement. And, a lot of us are here because our heroes are Galileo and Newton. So my point is that the space sustainability is a serious problem, but we have everything we need to do it if we get together. So NorthStar and I are really proud to be a small part of that solution. So with that, I will stop here. Thank you for listening to me. Merci beaucoup.
So we have about another 10 minutes. We have 2 mics and a full room. What questions you have, please bring them forward. Okay, Fred versus Fred.
I'd like to ask you a question about what, in your opinion, what do you think is the dominant advantage of doing this optical LEO to other spacecraft detection as opposed to radar? Because as you mentioned, radar will continue to exist, maybe deploy across all latitudes. What is the biggest benefit?
Well,
benefits?
Yeah, good question, Fred. So getting above the clouds for radar makes no sense, right? So it's about getting farther away. Radar will, the return will degrade at the fourth power because of distance. And they can only track very low Earth orbit well. As far as you get high, it degrades, and you don't really get to the MEO and GEO orbit. The advantage to go to space is to cover it all somewhat independently of that. But of course, we also have a distance, degrading factor, but it's not as strong. And I think the denied territory problem is something that the radar folks do not have a solution for. And I know this by speaking with colleagues at the U.S. Space Force. Don't get me wrong, it's great what they do, we need them, but it's limited.
Do you see added resiliency in having multiple ways to detect the same objects, or different error bars from doing the observation from optics instead of from the ground with radar stuff, as one of the key motivations? Yeah,
we complete in a data fusion perspective. We get the plane of sky. Radar will get the radial distance, so that's very powerful complementary data set. But the idea of a constellation is space-based, and I think I skipped over that, but I meant to say it. We're going to be able to see an object at various places in its orbit. And by doing that, if you observe it over there, well, you kind of determine the radial direction, because otherwise the laws of physics would say that, if you got your state wrong over there, it shouldn't be there. So we kind of cover that from having multiple view. That's why we want multiple planes looking at the same object from different point of view all the time. And also, I didn't say it, but we're not claiming we're going to see everything and detect it. I mean, sometimes they're too fast, too faint. That's fine. We'll catch it another day. But on average, our simulations show that 75% of geometric hits are detectable.
Okay, I got a question.
Yep.
So in your quote, Richard, you said that NorthStar is looking toward a constellation, I think that's 24 satellites, you mentioned, dedicated to space traffic coordination. So what's the difference between coordination, or what's the gap between coordination and mitigation? You know, there's a shadow in there somewhere. And I guess the idea about being able to track all these objects is good to stay out of their way, but is there a way to actually mitigate the problem?
Yeah, so it's an interesting question. I think it's part of the coordination. It's just a topic I did not really address. So primary business is to track them and understand where they are, where they're going. But then there's also the piece of characterizing their orbit, and especially satellites that have maneuvering capability will react sometimes on their own, because automated collision avoidance is being developed today. So keeping track of this is an important piece of it. And at the end, this is an infrastructure that can be used to supply information to educate owner-operator of satellites on how to best perform their collision avoidance maneuvers.
Okay, before I ask one last question, then, anybody else? No. Earth orbits as
There's one there.
commons. It's a shared asset. It sort of seems to be analogous in some respects to climate mitigation. You know, the deterioration of our climate around the Earth is a global problem.
Mm-hmm.
That is very painfully influenced by vested national interests, especially short-term interests. So I wonder, with Earth orbits as a common asset, to what extent do national vested interests have a bearing on what nations agree to do internationally to coordinate and collaborate to minimize the problem you're talking about?
So if I understand you correctly, your question correctly, I think that nations have a critical role to play individually to set up standards. It's not because your neighbor is not going to do it that you shouldn't, or wait for it. Showing by example is a great, powerful tool, geopolitical tool that we have. It's not necessarily, in my opinion, easy to measure, but it is one of the best things we have. And I can give you the example of Luxembourg. You may know that NorthStar has opened an office in Luxembourg. This is a very small country, healthy, yeah, but not too big. But they have ambition, and they feel like we feel going there that they actually want to show an example and how to do it. So it's a great example, I think.
So a national vested interest would not be a bar to achieving international accords that could deal with the problem.
Mm-hmm.
In other words, national vested interest might in fact accelerate the establishment. You're talking about a bottom-up approach. So the really real bottom, I guess, is each nation's own framework, which then will hopefully to some extent integrate with other nations.
Yes, I agree.
And then you get the
Yeah.
very top, and it benefits from the bottom up,
Mm-hmm.
right?
Yep.
So I hope Canada will do its part.
Well, we have the brains to do it for sure.